Wait. Have you started? He'll give the key. He'll come again. Yeah, that's better. Yeah, sure. Hey guys, this is Parani from Great Learning, and I welcome you all to this session on decision tree algorithm. So let's have a quick glance at the agenda. So we'll start off with a quick introduction to machine learning. So we'll understand all the core concepts of machine learning, and then we'll dive into the decision tree algorithm. And then we'll implement the concepts of decision tree in both R and Python languages. All right, so we'll understand machine learning with this little example over here. So what do you see in this slide? What is this exactly? Well, it's a fish, isn't it? And what is this? Well, this again is a fish. And how about this? Well, this too is a fish. Now, how do you know all of these are fish? Well, as a kid, you might have come across a picture of a fish and you would have been told by your kindergarten teacher or your parents that this is a fish. And your brain learned that anything which looks like that is a fish, right? And that is how our brain functions. But what about a machine? Now, if I take this image of a fish and I feed it to a machine, will it be able to understand that this is actually a fish? Well, this is where machine learning comes in. So what I'll do is I'll take all of these images of the fish and I'll keep on feeding them to this machine until it learns all the features associated with this fish. Now, when I say all the features associated with this fish, so the features would be, let's say a fish has 2 eyes, it has 2 fins, it has a tail, it has gills, and so on. So this machine would learn all of these features associated with the fish. Now, once the training is done, it is given new data to determine how much it has learned. So what I'm basically trying to tell you is, first the machine is given training data. So first the training is done. And once it learns all of the features associated with the training data, it is given the test data. So this is where we are actually testing the machine how much it has learned. So we have given this new image of this fish to this machine, and we are trying to estimate whether this machine is able to correctly label this image as fish or not. So this is the underlying concept of machine learning. Right, and now that we know what exactly is machine learning, we'll have a look at the categories of machine learning. So machine learning can be broadly categorized into supervised learning and unsupervised learning. And we'll start with the first one, which is supervised learning. So in supervised learning, you basically have output variables and input variables. And these output variables are denoted with Y, and the input variable is denoted with X. So these output variables are also denoted as dependent variable, and this input variable is also known as an independent variable. And we are trying to determine how does an output variable change with respect to an input variable. Or basically, how does a dependent variable vary with respect to an independent variable? So this, what you see, Y equals Fx. So over here, Y would be the dependent variable and X would be the independent variable. And we are trying to determine, does Y vary with X or not? So again, supervised learning can be broadly categorized into regression and classification. So we'll start off with the first one, which is classification. So as you see over here, classification is basically the process of predicting the class of a new variable. Now let's take this example to understand classification better. So let's say we want to determine whether a person has cancer or not on the basis of whether the person smokes or not. So over here, whether the person has cancer or not would be the dependent variable, and whether the person smokes or not would be the independent variable. So we basically have a data set which would comprise of 2 columns, and one column would be the person, whether he has cancer or not, and then the next column would be whether the person smokes or not, right? And on the basis of this column, we are trying to determine whether the person has cancer or not. And this is basically the underlying method of classification. Now there is another method known as regression. So as it is stated over here, this method is basically used to find the linear relationship among different entities. So over here we have a dependent variable and we have the independent variable. So the dependent variable is denoted with y and the independent variable is denoted with x. Now what happens in regression is, let's say if I put in some random value of x, we would have to get a value of y for that. So this is what is basically known as regression. So for an arbitrary value of x, we are trying to find out a corresponding value of y. Now we'll head on to the most important part of a session, which is decision tree algorithm. So decision tree algorithm is a supervised learning method which is used for both classification as well as regression purpose, right? So you can both classify the data. Also, you can use it to find out what is the relationship between y and x. So let's understand the decision tree algorithm with this image over here. Now let's say I have this very simple question. So I want to know whether so my question is this: I want to know whether I can watch the movie Avengers or not. And for this, I have a set of decisions to make. So what you have is basically a tree-like structure, and this tree-like structure is decision tree over here. So we'll start off with the first condition over here, which is whether I like Marvel movies or not. And if I like Marvel movies, I'll come onto the left side of it, right? So it is yes. And then again, I'll check the second condition, which is if I am a fan of Robert Downey Jr. Now, if I am a fan of Robert Downey Jr., I will definitely watch Avengers. But if I don't like Robert Downey Jr., then I will not watch Avengers. Similarly, if I don't like Marvel movies, then the next condition would be whether I'm a DC fanboy or not. And if I am a DC fanboy, then I will definitely not watch Avengers because I'm anti-Marvel. So that is why I'll not go and watch Avengers. But on the other hand, if I'm not a DC fanboy, but I really like Scarlett Johansson, then I will go and watch Avengers. But if I don't like Marvel movies and I'm not a DC fanboy and I also don't like Scarlett Johansson, then I'll not watch Avengers. So this is what happens in decision tree algorithm. So we have a set of decisions which we are making over here, and on the basis of these set of decisions, we will go ahead and classify the data. So this is how the decision tree algorithm works. All right. So this is the basic idea behind decision tree algorithm. Now we'll have a comprehensive demo of this decision tree algorithm in both R and Python. So we'll start off with R. So we'll be working with this car seats dataset, and this car seats dataset is actually part of the ISLR package. So I'll go ahead and load this ISLR package first. So to load the package, I will type in library and then given the name of the package, which is ISLR. So I have loaded the package. Now this ISLR package basically has some datasets with it. So I'll have a glance at the different datasets which are part of this ISLR package. So as you see over here, these are all the different datasets. You got the auto dataset, caravan, car seats, college, credit, default, and so on. Out of all of these datasets, I want to work with this car seats dataset, which is basically about the sales of child car seats. Now I have to load this dataset. So this car seats dataset, as you see over here, this is actually capital C. Now I will go ahead and store this in a new object, and I will name that object in car seats over here. So this car seats, what you see, so this is small c and this is capital C. So I am loading this car seats dataset, which is part of the ISLR package, and I'm storing it into a new object and naming that object to be car seats. Now let me have a glance at this dataset first. So I'll just type in car seats over here, right? So this is my dataset. Now I'll have a glance at this dataset properly. Car seats. So we have the description of this dataset over here. So as you see, this is a simulated dataset containing sales of child car seats at 400 different stores. So we have 400 observations in total, or 400 records in total, and there are 11 variables or 11 columns in total. Now these are the different columns. So we've got the sales column over here. The sales column is basically the unit sales in thousands at each location. So this 9.5 would be 9.5 into 1000. So that would be around 9,000 sales. Then we've got comp price column, which is the price charged by competitor at each location. And then we've got the income column over here. So income column would basically tell you the community income level in thousands of dollars. Then we've got the advertising column, which denotes the local advertising budget for company at each location. Then we've got the population column over here. So this would tell you the population size in thousands. Then we've got the price. So price the company charges for car seats at each site. Then we've got the shelf location. So this basically tells you that there are three levels for the shelf location. Either it is good, bad, or medium. And this indicates the quality of the shelving location for the car seats at each site. And then you've got all of these different columns over here. So you've got the age column, education column, urban column, and US column. So you can just go through the description of this entire data set over here. So now that we have looked at the data set, we will start off by our data manipulation purpose over here. So now what you see is we have the sales column. So I want to add a new column which is dependent on the sales column. So let's say wherever the sales is greater than 8. So this 8 actually means 8,000. So wherever the sales is greater than 8,000, I want to denote it with high. And wherever the sales is actually less than 8, I want to denote it as low. And that is what I'm doing with this particular command over here. So I will use this if else clause, and over here I am checking if the sales, the number of sales is actually greater than or equal to 8. And if the number of sales are equal to or greater than 8, then I want it to be denoted with yes. On the other hand, if the number of sales are actually less than 8, then I want it to be denoted with a no. And I'm storing this in a new object and naming that object to be high. Now let me just show you the head of high over here. So I will type in high dot head. So let me go ahead and actually run this again over here. So let me check the class of this, class of high. Right, so this is actually a character. So I'll just put in high over here and I'll get maybe the first 5 elements. So what do you see? You have yes, 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 no, and no. Now let me compare this with this particular column over here. So as you see, the number of sales, it is 9.5. And since 9.5 is actually greater than 8, you have a yes value over here. Similarly, you have 11.2 over here. And since 11.2 is greater than 8, you have yes. Then you have 10.06, which is greater than 8. Again, you have a yes. After that, we have 7.4 and 4.15, which are less than 8. And that is why we have a no value over here, right? So we have basically created a new object where we are getting yes and no values on the basis of this sales column. So now that this is done, what we'll do is we will add a new object. So we will basically add this into this entire data frame, right? So I am using the data frame function over here. Using this, I will basically add this particular object into the car seats data frame, right? So I am attaching this new object as a new column into this data set, and I am storing it back to the car seats data frame over here. Now let me have a glance at car seats. So view of car seats. Now, if you have a glance at this data set, you see that we have added this new column, right? So let me show you the original data set view of, let me put in capital C over here. So this was the original data set which did not have the high column. And if we look at this particular data set over here, we have this high column over here. So all of these yes values denote those cases where the sales is greater than 8. And all of these no values denote where the sales value is actually less than 8. So we have done this, we have added a new column to this. Now this would be our dependent variable, right? So our problem statement for this particular data set would be, we want to understand whether the sales are high or not on the basis of all of these different factors. So I have created this column. Now since this column is actually based on the sales column, I will go ahead and remove this column. So let me copy this and let me paste it out over here. So as you see, what I'm basically doing is I am selecting all of the rows from this car seats data set, and I am also selecting all of the columns except the first column. That is why I put in -1 over here. So when I put in -1, I'll be getting all of the columns except the first column, and I am storing the result back to the same data set over here. So this is done. Now let me have a glance at this data set, view of car seats. So as you see, I have removed the first column, right? So the first column was the sales column, which I have successfully removed from over here. Now it's finally time to build our decision tree model. So we'll go ahead and build our decision tree. So to build the decision tree, we would require this tree package. So first you'd have to install the package. You'll click on packages, you'll click on install, and you will just type in tree over here. And when you click on install, the package would be installed. And since I have already installed it, I don't need to do that again. So I'll type in library and go ahead and load this package. So as you see, I have successfully loaded this tree library. So now that this is done, it's time to build my model. And as I have told you, the problem statement is this. I want to understand whether the sales are high or not on the basis of the rest of the columns, right? So I want to understand whether the sales are high or not on the basis of the income or on the basis of advertising or population or price and so on. So I will go ahead and build this model. So this tree package gives us this tree function, and inside this we are giving in two parameters. So the first parameter is basically the formula where we give in the dependent variable and all of the independent variables. So over here our dependent variable is this high column over here, right? So and the independent variable, so I have put in this dot symbol over here. So this dot symbol basically means that I am selecting all other variables as the independent variables except this particular variable over here. So let's take this tilde symbol. So whatever is given on the left side of the tilde symbol, all of those values are so that variable is taken as a dependent variable, and whatever values are given on the right side of the tilde symbol, all of them would be taken as your independent variables. So over here high would be a dependent variable and the rest of the columns would be your independent variables. And I want to build this model on top of the car seats data set, right? So this is the second parameter, and I am storing this in a new object, and I am naming that object to be tree model. So I have successfully built this model. Now let me have a glance at the summary of this model. So I'll use the summary function and I will pass in this object which I have just built. So summary of tree model, and this is what we have. So as you see, so this basically gives us the formula which we had just given, and there are 27 terminal nodes. Now there were multiple conditions, and after those multiple conditions we basically reached to this stage where we had 27 results or 27 conclusions. And then we've got the misclassification error rate and the residual mean deviance. Now you have to keep in mind that the misclassification error rate and the residual mean deviance have to be as low as possible, right? So we have successfully created this model. Now let me go ahead and also make a plot of this. So I will type in plot and I will pass in the same object over here, which is tree model, inside the plot function. So as you see, this is what we get. Now let me zoom this and let me count the number of terminal nodes. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27, right? So as it was stated in the summary, we have 27 terminal nodes over here. Now I will go ahead and add the text to this. So I will use the text function and I will pass in the tree model object inside this, and I have successfully added the text to this plot as well. So the first split is based on the shelf location column. So if the shelf location is bad or medium, then we'll come to the left side of this node or the root node. And if the shelf location is actually good, then we'll come to the right side of this. So as you see, this is the first root node. Now if the shelf location is actually bad or medium, we'll come to the left side. And here we are checking if the price is less than 92.5. And if the price is less than 92.5, we'll come over here and then we'll check if the income is less than 57. Then again, we'll check the competitor price, right? So over here, this is not clear. So the competitor price has to be less than something, and then we'll come down and we'll get this. Again, over here on the right side, we are checking if the population is less than 207.5. So whether the population is less than 207.5 or greater than 207.5, you basically get a yes. So this yes means that the sales are actually high. So in the terminal nodes, wherever you have yes values, all of those yes values indicate that the sales are high. And wherever you have no values, this indicates that the sales are not high. Similarly, if I come down to this part, so if the shell location is actually good, then my condition is whether the price is less than 135. And then again, I come down over here and I am checking if the price is, so here I'm checking whether it is based in US or not. So if it is not based in US, I'll come down to the left side. Again, I'll check if the price is less than 109. So the price is less than 109 over here, then yes, the sales will be high. Similarly, I'll come down if the price is less than 135, and if the income is also less than if the income is less than 46, then obviously since the income is less, the sales will not be high over there when people are not going to purchase a lot of car seats over there, right? And then on the other hand, if the income is actually greater than 46, then the number of sales would be high over here, right? So this is what the yes basically denotes. All right. So we have built this model, and we have also visualized this particular model over here. Now so this is we have done this without dividing our data set into the testing set and the training set. Now what happens when we don't divide the data into testing and the training set is we actually go ahead and overfit our model onto this data. Now to understand this, I'll give you an example. So let's say you have an exam tomorrow, and you have not studied anything at all. But then again, your friend comes to your rescue. He tells you that he has found he has basically bought the same question paper somewhere, or basically the question paper was leaked, and he tells you that there would be only 5 questions in tomorrow's exam, and he gives you the question paper, and you go ahead and basically learn or remember all of the answers for those questions. Now there are 2 scenarios. If in tomorrow's exam the same set of questions come in, then you are going to ace the exam, right? You are going to get 5 out of 5. But on the other hand, if none of those questions come in, right? So maybe you are fooled by your friend, or maybe your friend just took money from you, right? And it could also be the case that none of the questions come in. So you have only learned those 5 questions, but in the exam, there were totally new questions. And this is the case where you will totally fail. So that is why, this is what I'm trying to tell you. You have to divide your data set into training and testing sets. So first you go ahead and train the model. And once your machine knows properly about your data set, that is when you will go ahead and test its capacity. So it's extremely important for you to divide your data set into training and testing sets. And that is what we are going to do over here. So to divide the data set into training and testing sets, I am going to, I'll be needing the CA tools package. So I will go ahead and load this library, which is CA tools. Now the CA tools package would give me the sample.split function over here. So let me go ahead and use the sample.split function. So this again takes in 2 parameters over here. So the first parameter is basically the column on the basis of which you would want to split your data. So that particular column would be high, because there's a dependent variable, and the split ratio which I'm giving over here is 0.65. That is 65% of these records would have the true value, and the rest 35% of the records would have the false value. And this result, I am storing it in a new object, and I am naming that object to be equal to split tag. Now I'll just show you what is there in the split tag. So I'll actually show you maybe the first 5 results of this. You have true, false, true, true, true. Now this means that out of those, so as you see 0.65, so 65% of the records have been assigned this true value, and the rest 35% of the records have been assigned this false value over here. So now that we have the true and false tags over here, we are going to subset our data on the basis of these true and false labels. So wherever we have the true labels, we are going to select all of those true labels and store them into our training set. So inside this subset function, I am going to give the dataset, which is basically car seats. After that, I will specify that split tag is equal to true. So from this entire car seats dataset, wherever the value of split tag is equal to true, I am going to select all of those records and store them in the train set. Similarly, from this entire car seats dataset, wherever the split tag is equal to false, I am going to select all of those records and then store them into the test set. So now we've got the testing and the training sets ready. Now let me show you the number of rows present in the testing and the training set. So there are 260 rows present in the training set, and there are 140 records present in the test set. All right. So that was the splitting of our data into training and testing set. So now that this is done, we are again going to build our model. So now the difference is we are going to build our model on the training set and not on the entire data set over here. So I will use the tree function again, and this time this would be the function. Right, so the first parameter is the same. So I am passing in the high column, which is our dependent variable, and after the tilde symbol, I'll just put in a dot over here. So this dot means that all other columns except the high column would be my independent variables. And once I given the formula over here, I will given the data on which I want to build this model. So I want to build this model on top of the train set. So yeah, so I have successfully built this model. Now let me go ahead and clear this out, and I'll have a look at the summary of this. So summary of tree model, which I have just created. So as you see, now I have only 21 terminal nodes over here, and also I have the residual mean deviance and misclassification error rate given. All right, so I have built the model. Now let me go ahead and visualize this model. So plot of tree model. Let me again count the number of terminal nodes over here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. So as you see, there are 21 terminal nodes, which is what was stated in the summary of this. Now let me go ahead and add text to this. So text, I'll pass in tree model inside this, and let me zoom this over here. So again, as you see, the split is being decided on the basis of this shelf location column. Now, if I go on to the left side of this, so if the shell location is bad or medium, I'll come on to the left side. Next, I'll be checking if the price is also less than 92.5. So if the price is less than 92.5, I'll come over here, and then I'll check if the population is less than 207.5. So if the population is less than 207.5, again I'll come to the left side and I'll check if advertising is less than 9. And if this is the case, then the result would be no. That is, the sales will not be high. So for the rest of the two cases, it will be yes. Now let me come to the right side of it. So if the shell location is actually good, then I'll come to the right side of it and I'll check if the price is actually less than 156.5 or it is greater than that. So if it is less than that, then I'll check if the advertising is greater than 6. And if the advertising is greater than 6, then it will be yes. On the other hand, if the advertising is less than 6, then again I'll be on this side and I'll check if the age is less than 55 or greater than 55. So if the age is age of the people in the region is less than 55, then the sales of the car seats would be high. Else the sales of the car seats wouldn't be high. Right, so this is the sort of inference which we can draw from this. So we have added the text, we have visualized it. Now it's time to predict the values on top of the test set. So we have successfully done this, and to predict the values, let me just go ahead and copy this over here and paste this over here. So I'll be using the predict function. Now this predict function takes in these three parameters over here. So the first parameter would be the tree model. So this is basically the model which we have just built, and then the second parameter would be the test. Second parameter is basically the test set on which we want to build the model, and then we will give something new. So this parameter would specify what is the type of prediction that we want. And since we are doing classification, the type of prediction over here will be class. So I have used this predict function, and I am storing the predicted results in tree pred. Now I will go ahead and build a confusion matrix for this. So to build a confusion matrix, I will be using this table function. So as you see over here, inside this table function, I'll be passing in the actual values and the predicted values. So the actual values are stored in test $hi, and the predicted values are stored in tree underscore pred. Right, so I have created this confusion matrix. Now inside this, you basically have a tabular, you basically have a table, right? And you have this no and yes values over here. So what does this mean actually? So what this tells you is, out of all the records where the sales value was actually no, 66 of them were correctly predicted to be no. And this value tells that out of all the records where the value was actually no, 17 of them were incorrectly predicted to be yes. Then if we come down over here, out of all the records where the actual value was yes, 25 of them were incorrectly predicted to be no. Similarly, out of all the records where the actual value was yes, 32 of them were correctly predicted as yes. So this left diagonal which you see over here, this indicates all of the records which were correctly predicted. And this right diagonal indicates all of the values which are incorrectly predicted. So to get the accuracy, you will basically divide this left diagonal with all of the values present in this matrix. So let me do that over here. So I'll type in 66 plus 32 divided by 66 plus 32 plus 25 plus 17, and we get an accuracy of 0.7 over here. Now let me actually store this in ACC1 over here, and let me actually paste this over here. Right, so I have got the accuracy of this. Now I'll actually show you the plot of this again. Let me also add the text over here. So as you see, we have created a very big decision tree over here, right? So there are a lot of splits, and this is a tree which has overgrown. Now the question is this: do we actually need such a big tree to get the right accuracy? What if we'll get the perfect accuracy? Maybe, you know, if we end the splitting at this part or end the splitting at this part. So how do we find that out? So this is where you know, the mean deviance comes in, the misclassification error rate comes in. So there could be a case where if we stop splitting at this particular stage, the misclassification error rate would be the lowest. Or if we stop splitting at this particular stage, the mean classification error rate could be the lowest. So let's go ahead and find that out. So for that purpose, we will actually be building a cross validation for pruning our tree. So we have this cv.tree function, which is again part of the tree package. Now let me go ahead and use this function over here. So this takes in two parameters. So the first parameter is the tree model, or the model which we have built, and the second parameter is the function which is prune.misclass. So we are trying to prune this tree by finding out the right value of the misclassification error rate, and I am storing it into a new object, and that new object is basically cv tree. So now that this is done, right, let me just print out cv tree over here. So I'll just type in cv tree. All right, so just give me a second, guys. All right, so I have successfully given this over here. Now what you see over here is you have size, deviance, you have k value, you have method over here. So we started off with one root node, then we had two root nodes, 3, 5, and so on. And the initial deviance was 107, 82, and the deviance, it kept on decreasing. So this deviance kept on decreasing till 57, but after that, the deviance increased. So this would be the right value of the number of terminal nodes. So this is 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6. So this is where we'd have to stop, right? So when the number of terminal nodes are actually 9, that is when we would have the lowest value of deviance. So let me show you again. 1, 2, 3, 4, 5, 6, and over here you have 1, 2, 3, 4, 5, and 6, right? So at the value of 57, we have the lowest deviance. So let me check that out. So now what I will do is I will go ahead and prune the tree over here, and to prune the tree I am using this prune.misClass function, and in this prune.misClass function again I am passing in two parameters. So the first parameter is tree model, and then I will give the best to be equal to 9. That is, this will end when the number of terminal nodes are actually 9. So now that we have given this, we will store this in a new object and we'll name that object to be pruned model. Now I will go ahead and plot the pruned model over here. So plot of pruned model, and let me show you the number of terminal nodes over here. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So as you see, you have 9 terminal nodes over here. Now let me go ahead and also add the text over here. Right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. We have also added the text over here. Right, so again, the root node, the split is with respect to shelf location. So if the shelf location is bad or medium, we will come on to the left side of this, and then we'll check if the price is less than 92.5. And if the price is less than 92.5, then obviously the number of sales of car seats would be high. But on the other hand, if the price is greater than 92.5, then we'll come to the right side of it. And again, we are checking multiple conditions over here. Right, so this is how you can actually prune your tree, and you can figure out if, do we actually have to overfit our tree, or we can basically, cut out our tree at a particular stage. Now, earlier we had got an accuracy of 0.7 with the fully grown tree. Now, after pruning this tree, let me go ahead and predict again. So this time the model which I have built is pruned model. So I am trying to predict the values with respect to this pruned model on top of the test set, and the type of prediction is class, since this is classification, and I'll be storing this in tree_pred. Right, so I have done this over here. Now again, let me go ahead and build up this confusion matrix. So I'll be using the table function to build this confusion matrix over here. This again takes in two parameters. So the first parameter are the actual values which are stored in test$i, and then I will give in the predicted values which are stored in tree_pred. Now let me check in the accuracy over here. So as you see, this left diagonal would indicate all of those values which have been correctly classified, and this right diagonal indicates all of those values which have been incorrectly classified. So it would be 64 plus 40 divided by 64 plus 40 plus 19 plus 17, and we get an accuracy of 74%, right? So with a fully grown tree, we had an accuracy of 70%, but when we had actually pruned our tree, we got an accuracy of 74%, right? So this means that you don't have to overfit your tree. You can actually prune your tree at a particular stage, and that can give you a much better accuracy than what your fully grown tree can give you. So this is our confusion matrix over here, right? So yep, we are done with our first case study, where we were trying to classify whether the number of sales would actually be high or low on the basis of all of these different columns over here. So now that this is done, we will go ahead to the second part of it. So this, what we did was actually binary classification. Now instead of binary classification, I actually want to do multi-class classification. So to do multi-class classification, I'll be working with the iris dataset. So let me show you the iris dataset over here. I'll type in view and let me give in the name of the dataset, which is actually iris. So this is the iris dataset over here. So you've got all of these columns over here. You've got sepal length, sepal width, petal length, and the species column. Now, this is a multi-class classification because I am trying to determine the species of this iris flower with respect to the rest of these columns over here. So let me just show you. I'll use the table function and I'll type in iris dollar species. So as you see, we've got three different species. So the species of the flower either could be setosa, versicolor, or virginica. And there are 50 species of setosa, 50 species of versicolor, and 50 species of virginica over here. Right. So as I've told you, I want to find out the species of this iris flower with respect to the rest of the four columns over here. So now that this is done, again, I want to divide this entire iris data set into two parts, the training set and the testing set. So for this purpose, I'll not actually be using CA tools. I'll be using the caret package. So yeah, again, so to build the decision tree, we've got different packages. So either we can use the tree package, or we can use the party package, or we can use the rpart package. So the first example of the first demo was with respect to the tree package, and the second demo is with respect to the party package. So let me go ahead and load up this library. So I'll type in library of party over here. Right, so I have successfully loaded this party package. Now to divide this dataset into training and testing set, I will be loading up this caret package. Right. So this caret package gives me the create data partition function. So I'll be using this create data partition function, and this takes in three parameters. So the first parameter is basically the data set, the column on the basis of which I want to divide this data. Next is the split ratio. So I am giving the split ratio to be equal to 0.65, and list is equal to false. So if you want the result to be in the form of a list, you'll give in true, but I don't want the result to be in the form of a list. So that is why I'll set the list to be equal to false, and I am storing this result in a new object, and I am naming that object to be equal to split tag. So this is done. Now let me actually show you what do we have in split tag. So split tag, again, I'll show you the first 5 records. So what you see is you have 1, 5, 7, 8, 9. So out of these 65% records, right? So these are, so this row number 1, row number 5, 7, 8, and 9. These are part of those 65% records over here, right? So now that we have the those 65% records stored in split tag, so from the entire iris data set, I will select only those row numbers which are present in the split tag, and I will store all of them in the training set, right? So this is done. Now similarly, from the entire iris data set, I will select those records which are not present in the split tag, and I will store them in the test set. So now I have my testing and training sets ready. So n row of train, so I have 99 records in the training set, and then I'll also type in n row of test. So I have 51 records in the testing set. So I have my training and testing sets ready. So now I'll go ahead and build the model on top of the training set. So I'll be using the ctree function, which is part of the party package. So in this party package again, so in the ctree function, I'll give in two parameters. So the first parameter is again the formula. So I want to determine the species of this flower. So this is my dependent variable. So this is my dependent variable, and the rest of the columns would be the independent variables. And that is why I have given this species column on the left side of this tilde symbol, and I have given this dot on the right side of this tilde symbol. So species column is my dependent variable, and the rest of the columns are my independent variables. And I am building this model on top of the train set, and I am storing this result in the my tree object. So we have successfully built this model. Now I will go ahead and plot my tree. So let me remove this old plot over here, and let me build this up, and let's see what do we get. So this is what we have. So over here, the first split is being determined by the petal length column. So if the petal length is less than or equal to 1.9, then the species of the flower would definitely be setosa, right? So with a 100% guarantee, you can say that if the petal length is greater than or equal to 1, if it is less than or equal to 1.9, then the species of the flower would be setosa. On the other hand, if the petal length is actually greater than 1.9, then you'll have the second condition. So the second condition is if petal width is less than or equal to 1.7. So if it is less than or equal to 1.7, again you'll have the next condition where you'll check if petal length is less than or equal to 4.7. So if petal length is less than or equal to 4.7, then your species is definitely versicolor. On the other hand, if your petal length is greater than 4.7, then there could be two options. So there's a 59% or a 60% chance that it could be versicolor, and there's a 40% probability that it could be virginica. And on the other hand, if you have this petal width to be greater than 1.7, then you'll just come down to the right side of it, and you can say that with 90% probability the species of the flower would be virginica, and with 10% probability that the species of the flower is versicolor. Right. So we have built the model and we have also plotted the model. Now it's time to predict the values. Now to predict the values, again I'll be using this predict function, and this takes in this 3 parameters. So the first parameter is the model which you've just built. The second parameter is the test set on which we are trying to predict the values, and then we have the type of prediction, which is basically response, and I am storing this result in my pred object. Right, so we have predicted the values and stored the result in this my pred object. Now I will go ahead and create a confusion matrix again. So the actual values are stored in test $species and the predicted values are stored in the my pred object. So I have successfully created this confusion matrix over here. So let's understand this confusion matrix. So all of those records, so we see that all of those records where the species is setosa, they have been correctly classified as setosa. If we come to versicolor again, all of the records where the species of the flower was versicolor, all of them have been correctly classified as versicolor. Similarly, all of the records where the species of the flower was virginica, so out of those, 15 of them have been correctly classified as virginica, but 2 of them have been incorrectly classified as versicolor. Right, so you have only this part where there is misclassification. In the rest of the cases for setosa and versicolor, there is 100% correct classification. So let's go ahead and find out the accuracy of this. So that would be 17 plus 17 plus 15, which is your left diagonal over here, right? So all of these diagonals are present, so all of these values are present on the left diagonal. And then you will give in the rest of the values, which are 17 plus 17 plus 15 plus 2, and you get an accuracy of 96% with this model which you've just built. Right, now let's understand the problem with this model. So as you see, only 2 columns have been used for the prediction of the species of the flower. So only petal length and petal width have been used, but the rest of the columns have not been used. So that is why we are going to build this model again, where we'll use only petal length and petal width as our independent variables. So I am building my second model over here, and in this, species would be my dependent variable and the independent variables would be petal length and petal width. And I am building this model on top of the train set, and I am storing this result in the my tree2 object. So I have built this model. Now again, let me go ahead and visualize this. So I'll use the plot command and I will pass in my tree2 object inside this, and as you see over here, so this is what you get. So this is sort of the same plot which we've got from the previous one, right? So the only difference is, instead of using all the columns as our independent variables, we have only used petal length and petal width as our independent variables. All right, so this is done. Now we will go ahead and predict the values. So we have built the model. Now it's time to predict the values. So this time I am again predicting the values, where I am passing in the first parameter as my tree2. So this is the model which you have just built, and I am predicting the values on top of the test set, and the type of prediction is response, which I am storing in my pred2. So I have made the prediction. Now let me go ahead and create this confusion matrix. So I am passing in the actual values which are present in test $species as the first parameter, and then the second parameter, the predicted values, are stored in my pred2. All right, so again we have the same result over here. right? So instead of using all the columns, if we just use the petal length and petal width column, that is more than enough for us to determine what type of species this particular iris flower is. So that's quite an interesting observation, isn't it? Right, so we are done with binary classification. We are also done with multi-class classification. Now we'll go ahead and do regression with decision tree. And for that, we'll be working with the Boston dataset, and we'll be using a different function. So we'll be working with the rpart library over here. So this rpart basically stands for recursive partitioning. Right, and let me go ahead and load up this Boston dataset. So I'll be using this read.csv function, and I am passing in the path over here, and I am storing this in a new object and naming that object to be Boston. So let me just type in view of Boston in here, right? So this is my data set. Now let me just show you this data set over here. So this is also part of the mass package. So let me load up the mass package now. Let me put in this question mark and let me type in Boston over here. Right, so this is our Boston dataset, which comprises of all of these columns. So you've got CRIM, which is basically the per capita crime rate per town. Then you've got ZN, which is proportion of residential land zoned for lots over 25,000 square feet. Then you've got Indus, proportion of non-retail business across per town, right? So out of all of these, our column of interest would be this MEDV column. So this MEDV column stands for median value of owner occupied homes in $1,000. So I am trying to determine what is the median value of the house with respect to the rest of these columns over here. So in your free time, you can go through the description of this entire data set, right? So you have all of these columns and you can go through the description of this particular data set over here. So now that this is done, we have loaded the data set, we have understood the data set. Now it's time to divide this data set into training and testing sets. So for that, we would require the create data partition function, which is part of the caret package. So I am loading the caret package first. Once I have loaded the caret package, I am using this create data partition function. So again, I want to divide this dataset into two parts with the help of this. So on the basis of this MEDV column, and the split ratio which I'm giving is 0.70. So I want 70% of the records to be in the train set and 30% of the records to be in the test set, and I am storing this in split tag. Now I will just go ahead and take all of those records in the Boston dataset, which are so those rows which are present in the split tag, and store them in the training set. Similarly, all of those rows which weren't present in the split tag, I am selecting all of those rows from the Boston dataset and I am storing them in the test set. So I've got my training and testing sets ready again. So I'll type n row of train, and I see that there are 356 records. Now again, let me type in n row of test. So let me just type in n row of test over here. So I've got 150 records in the test set. So I have divided this data set into training and testing set. Now it's time to build the model on top of the train set. So I'll be using the rpart function, which is part of the rpart package. So the formula is pretty much the same, right? So the first parameter, I am giving the MEDV column as my dependent variable. I'm putting it on the left side of the tilde symbol, and I am taking the rest of the columns as my independent variables. And I am building this model on top of the train set, and I am storing this in a new object, and I am naming that object to be equal to my tree. So I have successfully built this model. Now I will go ahead and visualize the model which I've just built. And to visualize that, we have this package called as rpart.plot. And this rpart.plot package would give me the rpart.plot function, and I am passing the my tree object inside this. So let me see what do we get. Right, so over here, as we see, the first split or the root node is based on this lstat column. So we are checking if the value of L stat is greater than or equal to 7.7. And if it is greater than or equal to 7.7, then we come over here. Again, we check if L stat is greater than or equal to 15. If this is true, we'll do another check where we are finding out if the crime is greater than 6.3. And if that is true, your median value of a house would be $12,000. And if it is crime is not greater than or equal to 6.3, your median price would be 17. Now let's come to this higher end over here where the median price of the house is $46,000. So let's see how do we get $46,000. So first is your L stat value. So if your L stat value is greater than or equal to 7.7, if it is not greater than or equal to 7.7, then you will come to this side and you are checking if RM is less than or greater than 7.5. So if RM is greater than 7.5, then you'll come over here and you'll say that the median price of the house would be $46,000. Right, so this is the way how you are trying to find out the price or the median price of this house. Similarly, if I want this case over here, so L stat is not greater than or equal to 7.7, we'll come over here. Again, if RM is less than 7.5, we'll come over here. Again, if age is actually greater than 92, we will come on the right side. Then we will say that the price of the house would be equal to $42,000. All right. So we are done with the visualization part of it. Now we will go ahead and predict the values. So we have built the model. Now it's time to predict the values. So this takes in two parameters. So the first parameter is the model which we have just built. The second parameter is the data set on which we are trying to predict the values, which is basically the test set, and I am predicting the values on top of predict tree. So I have successfully predicted the values as well. Now that this is done, it's time for me to bind the actual values and the predicted values. I'll be using the cbind function. So the actual values are stored in this MEDV column of the test set, and the predicted values are stored in the predict tree object which we had just created. So I am binding these two and storing them in a new object and naming that object to be equal to final data. So I'll have a glance at this view of final data. So these are the actual values of the median price of the house, and these are the predicted values of the median price of the house, right? If the actual was 24, it was predicted as 25. Actual was 33, it was predicted as 31. So what you see, you basically have an error in prediction for all of these. And if we want to find out the average error in prediction, we have to get the root mean square error, right? Now again, so this is actually a matrix. So let me show you the class of this. So I'll type in class of predict tree, and you see that this is actually this is a matrix over. So this is actually class of final data. So I'll type in class of final data. So this is a matrix, and I have to convert this matrix into a data frame. So I'll select as dot data frame. I'll pass in final data into this, and I'll store it in a new object. I'm actually storing it into the same object, which is final data. Now let me check the class. So class of final data. So as you see, this is a data frame now. All right. So now I will go ahead and subtract the predicted values from the actual values, and that will give me the error in prediction. So when I subtract this particular value from this particular value, I will get the error in prediction, and that is what I'm doing. So final dollar predicted, and I have final dollar actual. I am subtracting these two, and I will store the result in something known as error. Now I will bind the error back to the final data which I have. So cbind final data, and I am binding the error to this, and I am storing this in final data. So view of final data. So actual values, predicted values, and I have the error in prediction over here. Now I will go ahead and find out the root mean square error. So this is what I have over here, right? So first I will take the square of the error. So final data dollar error, I will take the square of this. Then I will take the mean, so mean square, and when I take the square root, I will get root mean square error, and I am storing this in RMSE1. So let me show you what is the value of RMSE1. So I get a value of 4.99. All right, so this is my first model, and I've got the RMSE value or the root mean square error value to be equal to 4.99. Now, one interesting take over here is we are not actually using all of the columns over here, right? So we are only using LSTAT, RM, age, DIS, and crime. So instead of giving all of the columns, let me just use these particular columns and build the second model. So let me select this over here, right? So I am building this second model where my dependent variable is again MEDV, but my independent variables would be only LSTAT, and then I've got RM, after that I've got age, then I've got crim, and then I've got DIS, right? So have I included everything? I've got LSTAT, I've got RM, I've got CRIM, and age I've got, and I've also got DIS. So I have added all of these as my independent variables, and I am building this model on top of the train set, and I am storing this in a new model and naming that model to be equal to my tree 2. Right, so I have built this model. Now let me remove this actually, and yeah, so now let me go ahead and predict the values. So I'll use the predict function again. I will pass in my tree 2. So this is basically the first parameter, and the second parameter would be the test, because I want to predict the values on top of the test set, and I will store this in a new object and name that object to be equal to predict tree 2. Right, now I will go ahead and bind the actual values and the predicted values. So the actual values are basically the MEDV column from the test set, and the predicted values is basically this object predict tree 2, and I am naming this as actual, and I am naming this as predicted, and I am storing this in final data 2. Now I'll have a glance at final data 2. So view of final data 2, I've got my actual values and the predicted values over here. Right, now it's time to convert this matrix into a data frame. So I'll use this as.dataframe function, and I'll pass in final data 2 inside this, and I'll store this in final data 2. Now let me go ahead and calculate the error in prediction. So the error in prediction is basically actual minus predicted, right? So I'll type final $2 actual minus final data $2 predicted, and I will store this in error 2. So I have the error in prediction. Now let me go ahead and bind the error back to the original data, and I am storing this in final data 2 again. All right, so view of final data 2. So I've got the actual values, the predicted values, and the error in prediction. Now let me find out the root mean square error for it. So I'm taking the square of the error, then I'll take the mean of it, then I'll take the square root of it, and I'll store it in RMSE2. So let me print out RMSE2, which is 4.99. Let me also print out RMSE1, which is 4.99. So as you see, this is basically the same. Now instead of including all of the columns, if we just include these columns, we'll get the same particular result. So that is why you don't have to overfit your model. It's not necessary to build your model on top of all of the columns. So by visualizing, you got to know that if I just include these particular columns, then I'll get the same sort of accuracy, or I'll get the same sort of error in the model which I'm building. So this is an interesting inference, isn't it? Right. So we are also done with the regression part with decision tree classifier, and all of this was in R. So now we'll also go ahead and do the same thing in Python as well. So I have my Jupyter notebook opened up over here. So yeah, so first what we'll do is we'll work with the iris dataset, and we'll perform the same classification with respect to the iris dataset. So I would be needing the pandas package for this. So I'll be typing from so it will be import pandas as pd. Let me go ahead and load up the pandas package, and I have to read a CSV file. So pd.read_CSV, and the name of this dataset is iris.csv, and I will store this in a new object and name that object to be equal to iris. So I have stored this in iris object. Now let me have a glance at the head of this. So iris.head. So this is my data set, which we had already seen in our studio. Now we have to perform the same thing. So now I want to know the species of this flower with respect to the rest of the columns over here. So for this purpose, I have to separate out my dependent variable and the independent variable. So in Y, I will be storing my dependent variable, which is species. So I'll type in iris, I'll give in 2 square brackets over here, and inside this I will give in the species column. Similarly, I will store the rest of the columns in X, which would be my independent variables. So I have got sepal length over here, so sepal dot length, and then I've got sepal width, so I'll type in sepal dot width. After that, I'll type in petal length, and then finally I've got petal width, so I'll type in petal dot width. So I've got the dependent variable which is stored in Y, and I've got all of these independent variables which are stored in X. So this is done. Now it's time to divide the dependent and independent variables into train and test sets. So I will be needing the train test split. So I'll type from sklearn dot model selection. So let me just type in model selection over here. I would be from sklearn dot model selection import train test split. So let me just type in train test split over here. Right, so seems like I've got this twice. I have imported train test split. Now inside the train test split, I'll be passing in X and Y, which are my independent variables and dependent variables, and I will set the test size to be equal to 0.3. Now this would give me 4 results, which are X train, then I've got X test, after that I've got Y train, and then finally I have Y test. So X train, X test, Y train, and Y test. So this X train is basically the training set for the independent variables, X test is the test set for the independent variables, then Y train is the training set for the dependent variable, and Y test is the test set for the dependent variable. So this is done. Now I will go ahead and fit the model. So I'd have to import the decision tree classifier for this. So from sklearn.tree, I'll be importing the decision tree classifier, and let me go ahead and create an instance of this. So I'll type in DTC and I'll create an instance of decision tree classifier. Right, now it's time to fit the model. So I'll type in DTC.fit and I'll be fitting the model on top of the train set. So I'll give in X train and Y train over here. So I have successfully fit the model on top of the train set. Now it's time to predict the values. So I'll type in DTC.predict over here, and I am predicting the values on top of the test set. So DTC.predict, and I am storing this in X test, and I will basically store the result in ypred. So I'm predicting the values on top of the test set, and I am storing this in a new variable and naming that variable to be equal to ypred. Right, so this is done. Now I will show you the actual values and the predicted values. So the actual values are actually stored in ytest. So I'll type in ytest.head, and the predicted values are stored in ypred, but ypred is actually a numpy array. So what I'll do is I will show you the values, the first 5 values over here. So as you see, the actual value is setosa, which was classified as setosa. Then you got virginica, which was correctly classified again as virginica. Then you got versicolor, which is correctly classified as versicolor. Then you got setosa, which is again correctly classified as setosa. And then you got versicolor, which again is correctly classified as versicolor, right? So till now you got a 100% correct classification. Now to check the accuracy, what we'll do is we'll build a confusion matrix and we'll also calculate the accuracy score. So for this, I'll just type in from sklearn.metrics. I'll be importing, what do I have to import? I would need the accuracy score. And inside the accuracy score, I'll pass the actual values which are present in y-test and the predicted values which are present in y-pred. And we get an accuracy of 91%. Now let's verify this with the confusion matrix. So I'll go ahead and also import the confusion matrix over here. So let me just type in confusion matrix. I have loaded this. Now let me also just type in confusion matrix over here. So I'll type in confusion matrix. Again, I'll pass in the actual values which are present in y-test and the predicted values which are present in y-pred. So this is what we have, right? So you've this left diagonal again indicates all of the values which have been correctly classified, and the rest of the values are incorrectly classified. So now when you add 15 plus 16 plus 10 and then you divide it with 15 plus 16 plus 10 plus 4, you have an accuracy of 91.11, which is the same as this, right? So you are also done with implementation of this decision tree classifier on top of this iris dataset, and we get an accuracy of 91% for this. Now we'll go ahead and also work with decision tree regression. Right, so let me go ahead and cut all of this out from this. So this time I want to understand how does the sepal length vary with respect to the petal length of the iris flower. So sepal length would be my dependent variable and the petal length would be my independent variable. So I'll be storing sepal length in y. So let me just type in sepal dot length over here, and petal length would be my independent variable. So let me remove the rest of the variables over here. So I'll remove the rest of the variables from here. Right, so sepal length I am storing it into y, and petal length I am storing it into x. So I've got my y and x variables ready over here. So now that this is done, I will go ahead and divide this entire data set into training and testing set. So for this purpose, I'll type from sklearn.model selection. I'll be importing train test split again. And inside this, I'll be passing xtrain. Sorry, I just have to import this. So this will be from sklearn.model selection. And this has to be O and not P. So from sklearn.model selection, I am importing train test split. So again, I'll type in train test split over here, and I will basically pass in x and y, and I will set the test size to be equal to 0.3, and I will store this in, so this function will throw me 4 objects. And those 4 objects I'll be storing in xtrain, xtest, then I've got ytrain, and then I've got ytest. So I have all of these over here. So again, it's the same thing. So xtrain is the training set for your independent variables, xtest is the test set for your independent variables, ytrain is the train set for your dependent variable, and ytest is the test set for your dependent variable. So we are done with this as well. Now I will go ahead and fit the model, and to fit the model we actually have to load the decision tree regressor first. So from sklearn.tree, I'll be importing decision tree regressor, and now that I have imported it, I'd have to create an instance of it, and I will store that instance in DTR. So I am storing the instance of decision tree regressor in DTR, and now it's time to fit the model. So I'll type in DTR.fit, and I am fitting it on top of xtrain and ytrain. So I have also successfully fit this model. All right, Now it's time to predict the values. So to predict the values, I will type dtr dot predict over here, and I'd have to give in x test. So I'm basically predicting the values on top of x test, and the result I'd be storing in y pred. Right, so I have my predicted values. Now it's time to have a glance at the actual values and the predicted values. So y test, and so I'll get the head of this, and the predicted values are there in y pred. I'll have a glance at the first 5 rows. Right, so the actual value was 5.4, which was predicted as 5.7. Then we have 6.5, which was predicted as 6.1. 7.1 was predicted as 6.95. Then we have 5.3. Sorry, we have 5.3, which was predicted as 5.16, and then we have 7.2, which was predicted as 7.4. Right, so we had just had a glance at the actual values and the predicted values. Now let me find out the root mean square error. So now I will import. So from sklearn.metrics, I'll be importing the mean squared error. So I have successfully imported the mean squared error. Now it's time for me to find out the mean squared error. So I actually want the root mean square error. So let me import numpy first. So import numpy as np. Now I will get the square root. So np dot square root, and inside this I am passing in the mean squared error. So mean squared error of, I will pass in the actual values which are present in y test, and then I'll pass in the predicted values which are present in y pred. Right, so this will give me the mean squared error, and I'm taking the square root of this mean squared error, and I have an RMSE value of 0.391. right? So we have also successfully built the decision tree regressor on top of this data set, and the conclusion is this: we have a root mean square error value of 0.391. So guys, this brings us to this comprehensive session on decision tree algorithm. So we understood what exactly is decision tree. So to summarize it, decision tree is basically a tree based algorithm with which you can perform both classification as well as regression problems. So you have a series of conditions, and on those series of conditions you go ahead and make these decisions, and after that we implemented a decision tree classifier and decision tree regressor in both R and Python. Now before I sign off, let me actually open up the Great Learning page over here, and let me show you what we offer to you. So let me open up the BABI course, which is our business analytics and business intelligence program. So this is a program which has been ranked #1 in India, and it has been ranked #1 throughout consecutively for the last 4 years, and I'll tell you why. So our faculty members, we've got faculty, so we've got really esteemed faculty. We have Dr. P.K. Vishwanath, who has his PhD from Madras University. We have Dr. Muthukumaran, who has his PhD from Stanford University. And we have Dr. Abhinandan Sarkar, who has his PhD from Stanford again. So we had recently uploaded his full course on YouTube. So I will also show you Dr. Abhinandan Sarkar's full course. So let me just type in statistics for data science. So let me just type in statistics for data science over here. So this is Abhinandan Sarkar's statistics tutorial, right? So I mean, he is an amazing lecturer. So you can just go ahead and check out Dr. Abhinandan Sarkar's statistics tutorial. I'm pretty sure you'll be you would want to learn more about statistics after watching that video. And then we've got Dr. Bappa Dattya, who has his PhD from ISI. So we've got other really great lecturers over here. So if you are interested in doing an end-to-end course, so you can check out our page, and you can definitely contact us, right? So this is our PGP BABI course, and then we also have the AI ML course. So we have the artificial intelligence and machine learning course, which again is India's #1 artificial intelligence program. Now, isn't it wonderful? So our business analytics program and our artificial intelligence program, both of them have been ranked #1. And also, so we've got the same sort of faculty members over here. So all of these faculty members, so we've got also Arjun Jain, who has his PhD from Max Planck Institute, and he has an adjunct faculty at IIT Mumbai. Then we've got Professor Mukesh Rao, who is the director at Great Learning. We've got Dr. Amit Sethi, who has his PhD from University of Illinois, and he's also a faculty member at IIT Mumbai. So we've got a great bunch of faculty who will give you their best so that your learning experience is absolutely amazing. Right, so you can check out these batch start dates. So these are all of the classroom programs. So if you're in Bangalore, the batch starts on 5th of January. If you're in Mumbai, it starts in March. So these are the batch dates. You can check out our you can check out this link over here, right? So yeah guys, so if you are interested in doing an end-to-end post-graduation course, right, now this is not just a random course where you'll be learning a random stuff in 1 month of time. So this is a dedicated course. This is a dedicated course. This is a post-graduation course where you'd have to put in effort from your side as well. And once you're done with the entire course, you'll be getting the certificate from Great Lakes Institute of Management, and you will also get it from University of Texas Austin, which is which always ranks in the top 10 in the United States. And so that's amazing, isn't it? So you'll get a dual certificate, one from Great Lakes and one from University of Texas Austin, and this is available for both the programs. So it's the same for AIML and it's the same for BABI as well. So let me just show you the certifications over here. So where is the right? So again, so even for the BABI course, you'll be getting the certificate from both Great Lakes as well as University of Texas Austin. So again, I'm telling you, so this is a comprehensive course. It is a 11-month course actually. So this is not just a random course where we'll be teaching you a random bunch of stuff. This is a comprehensive course which has been designed in consultation with the IIT faculty members, with the University of Texas faculty members, with Great Lakes faculty members, and then we have come up with this 11-month post-graduation program. So if you are interested to enroll on this course, do check out this link. And so these are the contact details over here. So this is the phone number, and this is the email. You can check this out, right? So if you're interested, so to go to this site and check them out, right? So we have basically come to the end of the session, and I hope that you have comprehensively learned about decision tree algorithm, the concept of it, and how we can implement decision tree in both R and Python. So guys, I am signing off from my side. Thank you very, very much for attending the session.